Conceptually, it makes sense that when we have an extended object that can rotate about some pivot point, that such an object is going to have something that we might refer to as angular momentum. It's a little harder to see how an individual particle moving around through space, does that have angular momentum? So let's say that I have a particle that's moving in a straight line. Does that particle have angular momentum? And the answer is yes, though the value of the angular momentum may be zero depending on where I choose to put my pivot point. And so as an example for this, let's think about three different observers who are watching a car as it moves to the right. So I've got an observer sitting here at point A, an observer at point B, an observer at point C. The car is going to move to the right with a constant speed. What I want to know is, are there any of these observers that as the car is moving in a straight line at a constant speed, they happen to see the car having a non-zero angular momentum? What we'll care about is known as the line of motion. The line of motion is the line that lies along the line of the velocity vector. So in this case, what we notice is that the observer sitting at point B happens to be sitting at a point that lies along the line of motion, which means that for that observer, as they watch the car, they can sit there, watch the car move away from them, and their head doesn't have to move at all. If you're sitting at point A or point C, if you're one of the observers at either of those two places, to watch this car drive past, in some sense, you need to turn your head to watch the car move. So what that's indicating is that because you need to turn your head to watch the car as it drives in a straight line, that means that from your location where you are choosing to put the pivot, that particle is going to have a non-zero angular momentum. You can think of it as your head turning on your neck is indicating that from your perspective, where you sit at that pivot, you see angular momentum for that particle. So observers at points A and C will see this car as having a non-zero angular momentum. How do we calculate out the angular momentum for a particle then? Well, so what we're going to do is we're going to calculate out the angular momentum. We're going to use capital L to represent the angular momentum. And again, the magnitude of that vector is going to be given by the length of a position vector, and the position vector for the particle is going to run from where we choose to put the pivot to where the particle is located. I'm going to multiply that times the magnitude of the particle's linear momentum, so mass times its speed, times, again, the sine of the angle between these two vectors. So once I've drawn in R, I can redraw R and P from the same origin. So what I see is my position vector, my linear momentum vector. I know my linear momentum vector points in the same direction as the velocity vector, and that lets me see what angle phi is to do this calculation. Because I know what the magnitude of the linear momentum is, it's just mass times speed, I can go ahead and plug that in. And so I get that the magnitude of the angular momentum is going to be given by the particle's mass times the particle's speed times the length of this position vector times the sine of the angle between R and P. Now if I think about R sine phi, so this length times this sine term, if I think of that as a single quantity, what I recognize is that it's the component of the position vector that is perpendicular to the direction of the velocity. So what this tells me is that it's only the component of the position vector that's perpendicular to the particle's momentum that actually contributes to the angular momentum. Another way to think about this is that I know the line of motion lies along the line of the velocity vector. And so what I see is that this R sine phi, that distance, is nothing more than the perpendicular distance from the pivot to the line of motion. So I can calculate the magnitude of my particle's angular momentum by taking the mass of the particle times the particle's speed times this lowercase l, which represents the perpendicular distance from the pivot to the line of motion. So now that we've got our equation, if we come back to think about our car and our three observers, Well, again, as the car moves, there's its line of motion. If I think about my observer at point B, because it lies along the line of motion, that tells me that my little l, that perpendicular distance from the observer to the line of motion, is 0. Which is why my observer at point B says that the car has no angular momentum. For the observer at point A, there is some perpendicular distance from the observer at A to the line of motion. So as long as your observer doesn't sit along the line of motion, there's going to be some perpendicular distance, which means that there will be some angular momentum. And so again, I'll have the angular momentum as measured by the observer at point A is the mass of the car times the speed of the car times this perpendicular distance from the location at point A to the line of motion. Again, a right-hand rule is going to tell us that the direction of that angular momentum points into the page. For our observer at point C, again, same idea. Point C is not along the line of motion, so there has to be this non-zero perpendicular distance from that observer to the line of motion. That observer will calculate the car as having an angular momentum that's equal to mass of the car times speed of the car times whatever that perpendicular distance is from point C to the line of motion. Again, using our right-hand rule here, what we would see is that the angular momentum for the car, if you're standing at C, points up out of the page. So if you think about this as a picture where we're looking down, so a bird's eye view of us looking down on the car and these observers, then the angular momentum for the observer at point A will point into the screen, and the angular momentum for the observer at point C will point back up out of the screen at us.